All right, welcome everyone. This is the first time I've met most of you, but you guys have been meeting hopefully more often from now on. So yeah, it's great to meet you all. I'm Ambrose Bonnaire-Sergeant. We're going to talk about leveling up Clojure runtime specs, and you'll figure out what that means by the end. All right, so a, there's a great happening recently in Clojure in the last 5 years, which is this introduction of a spec. 5 years, it must be like 8 years now. It's so normal now, but there's really a division of how you program with Clojure before specs and after specs. And there's some similarities, but let's just simplify things to to prove a point. So before specs, you wrote a program and then you sat down and you thought really hard, how do I break this program? And you start writing examples and then eventually you find a problem and then you fix the program. So for example, say we have a function and we say that it takes an argument x and returns x, clearly does not, but let's just go with it. We'll say, okay, well, I think this, if I give it 1, it should return 1. All right, good. It does. If I give it hello, it should return hello. It doesn't. So that step 2 is over. Now we go back to fix the program. Well, okay, that shouldn't return 1. It should return x. And then we run our examples again, and we're done. So that was programming before specs. Uh, for the purposes of this talk. Okay. Programming after specs. You write the program. Step 2, write a spec. Step 3, stuff happens that you don't need to care about. That's the whole point. You get told what the problem is, then you fix the program. So the introductions of specs really starts a dialogue between humans, which I am representing with this mouth, because this is a dialogue, um, and a computer. I'm just going to call it a computer from now on, basically manual versus automatic stuff, you know. So the human can say, I wrote a program. All right, great. There it is. And the computer is very happy about this. And now the computer's like, I can check your program for mistakes if you give me a spec. And then I can be like, here's a spec explaining how this should work. And the program, the computer says, okay, I'm going to check your program against this spec. And whoops, there's a problem. Your program has a mistake. This is where it went wrong. And then the human can say like, whoa, let me fix that. Fix it. There, try again, please. And the computer can say, well, looks good enough for me for now. So this computer over here on the right, in Clojure, there's really 3 different ways you can make use of this computer. Uh, let's so first one is a library called Schema. Second is a library called Clojure Spec, which is where the word spec was sort of popularized from. And the third one is Malli. And for the purposes of this talk, these 3 libraries are pretty much are equivalently powerful. They do pretty much the same thing. What we're going to do in this talk is talk about something we can layer on top of these libraries to level up our specs. But first, let's have a quick introduction to specs. And I'm going to use Malli because it has a cool logo and it's pretty terse, so it fits on slides. All right. Yeah. So this is an address. This is where we are right now, down to the coordinates. We have a street, city, zip code, long latitude. This is called a value in programming. It's a map. And down here is what we call a spec. This is a spec for addresses down the bottom and an address up the top. And you can see that there's a correspondence between the spec and the value. The spec tells you what the map needs to look like. So it needs to have a street that is a string. We're on Washington Ave. The city that is a string, that is Madison. Zip code, uh, that, and long latitude, which is a tuple of two numbers. So this is the kind of thing that a spec can do at for values is uh, tell you the shape and uh, the contents of a value. So let's put this address spec up on the top left. What can you do with this spec? So the first thing you can do is validate values. You can ask questions like, does this value conform to this spec? So for example, here I've intentionally forgot to put a zip code in my address, and it doesn't conform to the address specification. So uh, Malli here will say, hey, this value is missing a zip code, and it's actually this value here that I'm pointing to needs a zip code. So that's validation. Another thing you can do is generate values. So you can say, create an example for this value. Create an example value for the spec. So here you can start to see some of the power of creating specs, which is random testing. So here, the street is clearly something that you would never in a million years write as a human. And you remember back in the first few slides, I was like, okay, let's test one hello. Imagine if I forgot to test hello. So this is started sort of the fundamentals of where the power of these spec libraries grow from. So they're going to try things, corner cases that you've never thought of, and find errors in your programs. So street is this really long gobbledygook city. Well, maybe I didn't even think of an empty city or a negative zip code. You know, maybe you should have like this. I did not prepare this. This was what Malli gave me when I asked it to generate an address. So, um, and yeah, long latitude, nothing much there, but some pretty interesting values there. Even just uh, asking for the smallest value you can ask for the spec. All right, but in Clojure, what we do most of the time is write functions, and a function takes something and returns something. So here we're taking an address and returning a string, and we're actually going to return the street of the address. And you can do two things with a function spec. The first is instrumenting the definition of the function, which is effectively redefining the function to validate the inputs and outputs. So it looks something like this. So instead of just returning the street address, the yeah the street of the address, first we're going to check that the input is an address and that the output is a string. So we've pushed in these specs so then they can be validated when we call this function. So say if we call this function with a street that's 52, then Malli is going to say, well, this should be a string, and in fact, you gave this to address street. At this point in this program, this is where it blows up. So that's the first way that we can use function specs. The second way is probably the most fascinating part of spec for me is fully automatic testing. And this is where the computer comes back. This is um, yeah, from the opening slides, this is the computer side of the dialogue. For the purposes of this talk, think of what I'm going to talk about in this exercise section. So what exercising a function does is you can use generate to generate an address. So you create out of nothing really, just for the spec, an input for the function, then you call the function, and then you make sure that the output is the right shape. So the computer's saying, oh great, I have everything I need to test this program all by myself. So let's just try this. Let's try generating a random address, random, random, and it's going to check whether the output is correct and the input is correct. And you can imagine if you leave this computer long enough, it's going to try a lot of different corner cases you've never thought of. And um, in the end, it worked. I can't wait to tell the programmer what a good job they did. That's what I hope Malli thinks of me when I write a good program. All right, so that was an introduction to Spec. We're going to move into the subject of this talk. And let's think about this particular dialogue. So Marley's sort of asking us, well, I can help you find even more mistakes if you give me a really specific spec. And I'm saying, oh, I want to tell you something specific about this program, but I don't think Malli or Schema or Spec supports it. So that's what this talk is going to be. It's going to uh, intro introduce a new kind of spec that um, allows users to be more specific about the specs on their programs and allows the computer to have a much more accurate instrumentation, well, ex much more accurate or interesting way of a specific way of testing the function. So I was saying at the beginning of the talk, we're leveling up specs. We're really leveling up function specs. So the spec we saw before was address to string. That's the kind of spec that we're interested in here. So by the end of this talk, I'm going to reveal the question marks at the top left, but I'll keep you guys hanging. All right, so sort of the theme that that holds this idea together is this concept of data flow. And one thing we do in programming a lot is we move things from one place to another, we put them in containers, we take them out, and we can sort of trace the way that certain values move through the program. And so for example, here's the simplest function I can think of that illustrates this. It's the identity function. This is the docstring for identity in Clojure. It returns its argument. So if you give A to identity, it returns A. If you give 1 to identity, it returns 1. If you give nil to identity, it returns nil. But the thing I want, the concept here is the fact that the A here is the A that you get back. The 1 here is the 1 that you get back. And the nil here is the nil that gets back. And this, just looking at identity itself, it seems kind of obvious, but I'm sure a lot of you can think of some more interesting functions where the data flow is much more complex, and we're going to get to some of those. So yeah, just keep this idea of data flow in mind. So how would we spec identity today? So in Schema, it would be, well, I've already, so in Schema and Spec, it's any to any. And in Malli, it's any to any. Now, let's compare this to the docstring. Returns its argument. So what hope are we giving the computer to be able to test whether the identity function actually returns its argument when we have a schema like this? Not much. So why does this matter? Well, all these functions are very similar to identity in the sense that they just move things around. And all these functions, and all these functions, these, and I'm not saying, so these are all functions that are in Clojure itself. I'm not saying that we need to spec all these functions because they're probably fine, you know, but any functions like this that maybe we would build, we're going to build on top of all these things. And maybe if we're building a website, we don't care about this, but you're going to you're going to use a library that does care about this. So Spec and Schema and Malli, it's really, I think of being for the working programmer first, like the front lines. And I'm a library person. I love making tooling. So this idea isn't directly relevant if you're doing data science or um, writing creating a website. But uh, you, if you're doing that, you want to make sure your libraries are actually correct. So this is going to be a tool that library developers can use to hopefully, we can all stand. I don't know what the expression is. All float up. You know what I mean? It's the first Ambrosism of the day. All right, so let's go back to identity, and we'll do some more interesting functions later. But this is for illustration. So I'm saying that I'm going to give a more specific spec for identity that lets the programmer actually say in the spec that it returns its argument and that the computer can actually test that it returns its argument. So let's brainstorm some of the different specs we could give to identity. And let's use schema syntax for now. Well, this isn't even schema syntax. It couldn't fit on on a slide. This is more like type closure syntax. But um, so any to any, I guess technically, if you give anything to identity, you get back anything. This is a good, maybe not sufficient uh, uh, spec. So if you give it an int or a bool, you're going to get an int or a bool back. Fair. Same with ints. If you give it an int, you get an int back. If you give it a bool, you get a bool back. And here's the kicker. If you give it one, you get one back. So the general idea behind this, the theme of this talk and leveling up specs is that we're going to package up all these specs into a single spec that's going to look more like this. It's going to say for all specs X, choose any which one. Identity is X to X. And one of the coolest things I learned during my PhD was this little trick. When you look at a type like this, a spec like this, if you count the number of arrows the variable is to the left of, if it's odd, it's an input, and if it's even, it's an output. And then you draw inputs to outputs, and you can see the data flow that that we were talking about. So um, I guess I won't bog everything down with, but if you want to try it at home, try it, or But I'm just going to draw the arrows. So using that, like, there's the data flow. That's it's right there that it returns its argument, in a sense. Um, all right, so let's get a bit more concrete, right? A few years ago, I made this prototype on top of one of the Clojure specs, uh, and I released it as type CLJ spec. And this is the library that I'm going to sort of show off as the prototype of this idea. And my hope for this talk is that people take this idea and run with it. Maybe it'll land in actual, um, you know, mainline branches of these libraries, or because I had an interesting time sort of bolting it on. Um, so with that out of the way, let's show what the identity spec looks like. So again, this is the pseudocode for the spec for all specs X, X to X, and here's the data flow. And then here's the spec for identity that actually checks whether it returns this argument. And if you want to check out this library, it's at tinyurl.com/type dash clj dash spec, or check it out at the type Clojure GitHub page. But this actually isn't that much different from the actual spec you would give to identity. In fact, it's just these first few lines. It's only a couple of lines longer. But I'm not actually going to ask you to try and understand the spec. I'm just going to draw these arrows. So here's the arrow that I was talking about. This X goes to X. So um, yeah, I'm not going to go into like a lot of detail about how this works under the hood. Maybe we can do questions afterwards. But the thing we can do now is rely on the computer to be able to tell a good identity function from a bad identity function. So I've just pasted this from the test suite of type CLJ spec. So this is saying that the identity function is of this spec, and that this function that returns nil all the time is not. And if you've used spec before, you'll know that this is different from any to any. Like this is actually any to any. This this tells us that the library has checked whether it returns its argument. And sort of if we zoom out, like what is actually happening here? So a few slides ago, we went from the left to the right. So what this is very similar to the dialogue, but sort of the sides are flipped. So as a programmer, I can say, I'm going to write this. And then the computer can say, well, I'm going to treat them as if they're all these things. So we can write a spec that is more precise, easier to convey, easier to read in some ways, and allows the computer to uh, check things much more accurately. All right, so that's the gist of the idea. I'm just going to sort of hammer this home with a couple more examples of increasing complexity until your brains break, or you can't wait to break the library. You know, one of those two. So this is going to be just let it wash over you. There's going to be arrows everywhere. You know. All right, the next candidate is map. So map applies the function to each element of the collection. So if we have 1, 2, 3, and we add 1 to each one, we get 2, 3, 4. So the data flow is you take 1, you add 1 to it, and you get 2. So there's 2 arrows. You take 2, add 1 to it, and return 3. Take 3, add 1 to it, return 4. So how do we spec map currently today? In Schema, it looks like this. You take a function of any to any and a collection of any, and you get anything. In Spec, it's the same thing. And in Malli, it's the same thing. And like we did the identity function, let's compare the two, sort of the informal specification and the formal one. There's really not much of a relationship. There's not much of a hope we're giving to the computer to be able to tell a good map from a bad map, you know, because there's no encoding of this applying a function to each element in the spec itself. All right, so let's use the same strategy to build up the new spec for map. So this is a good spec for map. If you have a collection of anything, well, your function needs to take anything, and you return anything, and then you get anything out. Doesn't matter if yeah. But if you have ints, your function needs to take ints and return strings. But okay, if you didn't follow any of that, here's the really obvious one. Okay, so if you have ones, you need something that can take 1 to 2, and then you get 2, right? And this is the sort of gives the game away. where we can summarize this as for all specs, x, y um, takes x, function from x to y, a bunch of x's returns y, so, y's. And we can do the same trick again, count the number of arrows that we're to the left to, and I won't bore you with it. I'll give you the pretty picture. Here's the first one. So this is actually applies the function to each element, this arrow here. And I guess the second arrow here is implicit, that you return um, the result of that application. All right, so let's put the schema up here and um, the pseudo schema and write the actual schema. So here are the data flows again. Here's the actual schema, and if you have time to look at it, and I don't know, it I guess it doesn't matter the specific details, but you can believe me that this spec looks pretty similar to the one that you would give to map, except we've sort of changed the any's to x's and y's. So the first data flow is from this collection to the input of the function, and the second one is between the y's. And the really cool thing is that now we can automatically, for some, we can automatically detect some bad implementations of map. So this first one is asserting that map is a correct instance of the map spec, and this passes. This is good. Now this second one is an intentionally bad implementation of spec of map, which it first maps things, but then obliterates the return value by just coercing everything to string. And if you think about the any to any to the really general spec, like this actually is this is totally fine for that spec. This will pass. But let's get the punchline again. But um, the punchline is that actually the computer here, type CLJ spec, can actually tell you that this is a bad implementation of map. And I didn't put the actual output, but it'll tell you that it's not this particular spec. It's actually the counter example you get is a spec. And again, we went from left to right, how we got this spec, but what happens under the hood, we go from right to left. We're on the right, we're writing this in the really big syntax that we saw before. I'll write this, and then I'll check these. And if you're interested, just as a side note about how instrumentation works, um, here's this any to any one is the spec that you'd want to instrument as well. So the way you get that from this spec is that you instantiate the x and the y with the most general spec that you have, and then this is a very versatile spec. You can get both the instrumentation spec and a much more powerful exercising spec, at least in theory. The in practice, spec is not quite that flexible, which is what I'm hoping to achieve in this talk by, having the library writers and people in charge think about this problem. Like, why can't we write this and get all these goodies? All right, this is going to be the last example. I think uh, if there's one after this, it's going to be pretty crazy, like transducers or something like that. Uh, but if you are interested in that, I would recommend you look at the README for this. Spoilers, it can check transducers. But comp is a function that is, so identity was simpler than map in some way because map is a function that takes a function. So comp is a function that takes a function, in fact, two functions, and returns a function. So it's even more to a higher order. You've got to have your thinking cap on if you need to think about how to, if we go back to the second slide, well, do I give it one or hello or a function or how, this is where the power of offloading that to spec really comes into play. All right, so we're going to draw a bunch of arrows about the data flow here. It's actually not that bad, but it gets a little messy. So we get an X here, and then you see at the end of this spec, it says applying G then F. So we apply G, and then apply F, and then the output of F, I guess, again, implicitly, is the output of the entire function. And again, how do we write the spec for comp today? It looks like this. F takes anything and returns anything. G takes anything and returns anything, and it returns a function that needs to take anything and return anything. And this is how you'd write it in Spec, and this is how you'd write it in Malli. And comparing to the informal spec that says returns a function that applies G then F, we're giving there's no hope that the computer is going to tell us whether my implementation of comp applies G then F, or if your does, or F then G, or forgets a G or an F. This is just anything goes, except for some very basic invariants. All right, so let's again build up the new spec for the more accurate spec for comp. So here's one valid spec for comp. Here's another one, and here's the one that gives the game away. If you have G that goes from 1 to 2, and F that goes from 2 to 3, then you can go from 1 to 3. So if we summarize these all in a spec, we get this. For all specs X, Y, Z, takes F that goes from Y to Z and a G that goes X to Y, and then you get a function that returns X to Z. And if you're like me, that didn't mean anything. So that's why I love this trick of how does this work? Well, count the arrows. First arrow, the input is actually over there. Isn't that cool? The input is over there because it's to the left of an odd amount of arrows. And then if we link the Y's up, it goes, well, I guess the first note with the first arrow, if we read the spec, applying G, okay, good, we've applied G, and then F, we've applied F, and the return is again left implicit in this, All right, and so what does the actual spec look like? So let's put the pseudo spec up here and have our awesome data flow arrows. Um, this is what it looks like. And for some reason, I've changed X and Y and Z to A, B, and C. Let's pretend, yeah, that it's 0, 1, or 2 or something. Uh, but let's forget about the details of this spec. It's basically that, but let's draw the arrows. The first arrow is that it applies G. So we're taking this A and giving it to G. You can see on the start of that line, that's G. And then F. So that's F. And you can see F is tagged next to the cat. And then the last part is you return the return value of F. All right. Now this is awesome. This really shows the power of as you build up these functions that take functions that take functions, uh, that actually this gets more powerful, at least in my opinion, in my thinking, like I would more readily use these kinds of specs the more complicated a function is. So, and if anyone's ever used comp before, you'd know that I'm greatly simplifying what comp actually looks like. Um, and it would actually, if you had to sit down and write it, it would be pretty tough to even write it, let alone think of all the ways you could test it. Imagine if you could write it and then have, the computer give you a thumbs up if you've actually done it correctly, right? So this is sort of the dream, and this is starting to the part of the realization of that dream. So, okay, so the spec says applies G then F. Well, this first one, it applies G and then applies F. It takes an F and a G and applies G then F. So this is good. And then this second one applies F and then G. And the computer says this is not a good implementation, and it'll give you a spec that doesn't, um, that it that this function should conform to, but doesn't. And I should have put the actual spec down there, but it'll look something like, um, it wouldn't have like ints or anys or things. It would have like a very specific, it would be more like that 1 2 2 3 1 3 thing. It'd be like, oh yeah, like basically putting gen sims through your program. And that's sort of part of the simplicity, is that you can sort of get a lot of this by today using spec, by writing the last spec on each, the left hand side of each one, the most specific one. So identity takes 1 to 1, for example. And uh, but I guess you don't have to now. uh, and now the more I think about it, this is a better approach. All right. All right, so what are we left with? We're left with, um, the user being able to write this and being able to and enable the computer to check all these, and uh, essentially allow the computer to help us see if we actually implement this spec correctly. All right, so back to, let's wrap this talk up. So we've been talking about leveling up function specs, and it's not a derogatory thing. I'm not saying that let's improve them. I'm literally saying we're going an abstraction level above. This is spec is a concrete, all these spec libraries, they're a great foundation to build on. So one way to think of what this is specs for specs. So it's like a meta-linguistic sort of leveling up. So all right, so to to summarize the talk, uh, if we have specs for specs, computers can be like, now with specs for specs, I can help you find even more mistakes. And the humans can be like, specs for specs, help me better explain my program. All right, thank you.